All right, welcome again. Oops, my mic's a little hot here. Let me fix that. All right, welcome again to Good Choices. Um, Let me make sure that my mic is set correctly. So I've got my output to my headphones and my input to the nice mic. Thank you very much. Or thank me, I guess. All right, so moving on to 102.1. We just finished up our system architecture topic. So we looked at started off really strongly with the kernel modules, learning what that was. It's kind of like the drivers. And we learned about booting up the system. We learned about service managers. Now we're on to Linux installation and package management, and we're going to start with design. Design hard disk layout. That's the objective. So introduction in order. So to succeed in this objective, you need to understand the relationship between disks, partitions, file systems, and volumes. Think of a disk or storage device, since modern devices do not contain any disks at all, as a physical container for you data. So it looks like there's an error here. Instead of saying for you data, it should say for your data. I've expressed multiple times on this channel, there's this really funny meme where they say, hey, look at the documentation, and then the documentation is a Lego with 3 parts connecting to a Lego with 4 parts, and the documentation clearly says to collect all 4 parts of the 3-part Lego to all 4 parts of the 4-part Lego. So it's like, I hope this isn't a sign. Little typos like that bother me, but let's continue. Before a disk can be used by a computer, it needs to be partitioned. A partition is a logical subset of the physical disk, like a logical fence. Partitioning is a way to compartmentalize information stored on the disk, separating, for example, the operating system data from user data. Every disk needs at least one partition, but can have multiple partitions if needed. The information about them is stored in a partition table. This table includes information about the first and last sectors of the partition and its type. Still a little bit hot here. I'm going to move that down. As well as further details on each partition. Inside each partition there is a file system. The file system describes the way the information is actually stored on the disk. This information includes how the directories are organized, what is the relationship between them, where is the data for each file, etc. Partitions cannot span multiple disks, but using the Logical Volume Manager, LVM, multiple partitions can be combined, even across disks, to form a single logical volume. Logical volumes abstract the limitations of the physical devices and let so there's the R that was missing before, they put it onto this instance of YOU, let you work with pools of disk space that can be combined or distributed in a much more flexible way than traditional partitions. LVM is used in situations where you would need to add more space to a partition without having to migrate the data to a larger device. In this objective, you will learn how to design a disk partitioning scheme for a Linux system, allocating file systems and swap space to separate partitions or disks when needed. How to create and manage partitions and file systems will be discussed in other lessons. We will discuss an overview of LVM in this objective, but a detailed explanation is out of scope. This is great. I actually remember learning about this when I was in my 2-year degree, 2013 to 2015, and I feel like I never really like, I don't know, like, I feel like that degree, you know, I wouldn't have gotten, like, it was a great way to launch my career, but I feel like it's not, like, if I get this LPIC, like, I'm set up to succeed at the LPIC, but I'm not necessarily set up to get hired with only that degree. So, like, this is confirming, maybe I have confirmation bias, but anyway, I'm grateful that I chose to study for this one. So let's keep on going. Mount points. Before a file system can be accessed on Linux, it needs to be mounted. This means attaching the file system to a specific point in your system's directory tree called a mount point. When mounted, the contents of a file system will be available under the mount point. For example, imagine you have a partition with your user's personal data, their home directories containing the directories /John, /Jack, and /Carol. When mounted under /home, the contents of those directories will be available under /home, /John, /home, /Jack, and /home, /Carol. The mount point must exist before mounting the file system. You cannot mount a partition under /MNT, standing for mount, /user data, if this directory does not exist. However, if the directory does exist and contains files, those files will be unavailable until you unmount the file system. If you list the contents of the directory, you will see the files stored on the mounted file system, not the original contents of the directory. File systems can be mounted anywhere you want. I'm going to need a glass of water. Let me finish this up. However, there are some good practices that should be followed to make system administration easier. I'm going to get to here and then go get a glass of water. Traditionally, /MNT was the directory under which all external drives would be mounted, and a number of pre-anchored anchor points for common devices like CD-ROM drives, which would typically be /MNT /CD-ROM, and floppy disks /MNT /floppy existed under it. Oh, and I forgot about this. So this little menu pops up. This is ChatGPT. So like I have ChatGPT tools. So like this polish tool. It will tell you. So we could make this whole thing easier to read using that polish tool. The other thing we could do is explain code if we see it. We can ask questions about the text, and then if it's in another language, we can translate it. So yeah, I talked about that tool in my last one, a useful tool. Moving on, this has been superseded by /media, so which is now the default mount point for any user removable media. For example, external disks, USB flash drives, memory card readers, optical disks, CD-ROM, floppy, connected to the system. So instead of having separate folders for each external device, now you have one device /media that contain your external devices. On most modern Linux distributions and desktop environments, removable devices are automatically mounted under /media, /user, /label when connected to the system, where user is the username and label is the device label. For example, a USB flash drive with the label flash drive connected by the user John would be mounted under /media, /John, flash drive. The way this is handled is different depending on the desktop environment. That being said, whenever you need to manually mount a file system, it is a good practice to mount it under /MNT, even though you can mount it anywhere. Just keep it with the other ones so you don't get confused about that. The specific commands to control the mounting and unmounting of file systems under Linux will be discussed in another lesson. So let's do this. This is going to be interesting, and then I need a glass of water. So we're going to highlight this sentence here. Okay, and then we're going to go to ask. Which is here, the question mark, of course. So, and now, so the statement suggests that when manually mounting a file system, it is considered good practice to mount it under this directory. From a technical standpoint, the MNT directory in Linux and Unix systems is commonly used as a mount point. It provides a standardized location. So here we go. Here's the answer. By following this convention, system administrators can maintain a consistent directory structure and organization. It helps in avoiding confusion and makes it easier to locate and manage mounted file systems. Additionally, mounting file systems under the standardized /MNT folder allows for clear separation. And when I say folder, it's because I'm a Linux. I've used Windows mostly, so it's a directory. Allows for clear separation between the operating system's core directories and the temporary or external file systems that are mounted. This can help prevent accidental overwriting or interference with critical file systems. Overall, the suggestion to mount file systems under /MNT when manually mounting them aligns with standard practices and can contribute to a well-organized and manageable file system structure. Wow, powerful stuff. Again, this is, so I'll go to my extensions here. It's called, where is it? Chat GPT box. I can't recommend this extension enough. We can see just how powerful it is for reading text like this. Yep. All right, so keeping things separated. I'm going to take a break for that glass of water. I'll be right back. Okay, I'm back. Let's keep moving on this. So the next section is keeping things separated. On Linux, there are some directories that you should consider keeping on separate partitions. There are many reasons to do this. For example, by keeping bootloader related files stored on /boot on a boot partition, you ensure your system will still be able to boot in case of a crash on the root file system. Okay, so if you lose all your files, like a partition gets corrupted or something, and you have a second partition, then if you have used that second partition to have all your boot files on, then you can still boot your system because you won't lose those files. So that's really the power in keeping things in a separate partition. You kind of, it's like you can almost think of like the Titanic or like a boat on the water. Like if you have like the boat designed so that the hull gets fractured and starts leaking in water, but your boat is in multiple partitions, so it's like the boat doesn't sink because it's just like one part of the hull fills in with water, but like it's separated out into multiple parts, so like you only have like 1/16 of your partitions on your boat flooded in with water, so you've got 15 out of 16 perfectly buoyant and usable sections of your boat, enough for you to keep, for the boat not to sink. So keeping users' personal directories under /home on a separate partition makes it easier to reinstall the system without the risk of accidentally touching user data. Keeping data related to a web or database server usually under /var on a separate partition or even a separate disk, makes system administration easier should you need to add more disk space for those use cases. There may even be performance reasons to keep certain directories on certain partitions. You may want to keep the root file system here on a speedy SSD unit, and bigger directories like home and var on slower hard disks, which offer much more space for a fraction of the cost. So yep, that's a really good thing. I want to ask, this part I don't remember reading so much. Let me read this one more time. Keeping a user's personal directories under /home on a separate partition makes it easier to reinstall the system without the risk of accidentally touching user data. Keeping data related to a web or database server, usually under /var, on a separate partition or even a separate disk, makes system administration easier should you need to add more disk space for those use cases. So let's see what the AI says about this. So I don't need to right click, I just need to highlight. Menu pops up automatically, and then I can hit ask. So the content you provided, and it's got to generate first, discusses the benefits of keeping certain directories on separate partitions in a computer system. It suggests that separating users' personal directories, typically located under /home, from the system directories can simplify the reinstallation process without risking the accidental loss of user data. Additionally, it mentions that storing data related to the web or database services, usually found under /var, on a separate partition or disk can facilitate system administration, particularly when additional disk space is required for those specific use cases. The content also highlights potential performance advantages of partitioning directories. It suggests that placing the root file system, which is denoted here, on a fast SSD solid state drive can enhance overall system speed. In contrast, larger directories like /home and /var could be stored on slower but more cost-effective hard disks, offering ample space. So overall, the content presents valid reasons for partitioning specific directories based on various considerations such as data protection during system reinstallation, ease of administration, and potential performance optimization. So those are the three reasons you'd use partitions: data protection, ease of administration, and performance optimization. Partitioning can help achieve better organization, data management, and system efficiency in specific use cases. All right, so next is the boot partition. And I think I need a quick break here. I'll be right back. All right, welcome back. So next we're going to read about the boot partition, which is /boot. Let's take a look at the boot partition before moving on my home lab. All right, so here's the boot partition. See a lot of .mod files and a lot of .efi files. Should know what those are based on the prior reading. The boot partition contains files used by the bootloader to load the operating system. On Linux systems, the bootloader is usually grub2, or on older systems, grub legacy. The partition is usually mounted under /boot, and its files are stored in /boot /grub. Let's take a look at that. There we go. These are the bootloader files. I don't see any indication that this is grub2. I guess I could take a look at the CFG file, config file for that. Let's do that. So cat boot grub.cfg. Okay, so I can't tell if it's grab version 1 or version 2. Probably version 2. It's usually version 2. One thing I could do though that would be really cool. So let's just ask. How can I determine if my system uses version 1 or version 2 of uses grub v or grub 2 or grub? Okay, so we can take a look at so if we want to determine whether it uses the current or the legacy version, here's the command we need. Oh, so we look for the grub.cfg. Yep, I was on the right track. If we see it, then that means it's using grub 2. If it's not there, then the it's a .conf file for the legacy version or a menu.lst. So the presence or absence of grub.cfg is a key differentiator between grub2 and grub legacy. Keep in mind that this method assumes so we're using grub2. Alright, moving on. Technically, a boot partition is not needed, since in most cases grub can mount the root partition / and load the files from a separate / boot directory. However, a separate boot partition may be desired for safety, ensuring the system will boot even in case of a root file system crash, or if you choose to use a file system which the bootloader cannot understand in the root partition, or if it uses an unsupported encryption or compression method. The boot partition is usually the first partition on the disk. This is because the original IBM PC BIOS addressed disks using cylinders, heads, and sectors, CHS for cylinders, heads, and sectors, with a maximum of 1,024 cylinders, 256 heads, and 53 sectors, resulting in a maximum disk size of 528 megabytes. Under MS-DOS, it's only 504 megabytes. This means that anything past this mark would not be accessible on legacy systems unless a different disk addressing scheme like logical block addressing, also known as LBA, was used. So for maximum compatibility, the root partition is usually located at the start of the disk and ends before cylinder 1024, which allows for 528 megabytes, ensuring that no matter what, the machine will always be able to load the kernel. Since the boot partition only stores the files needed by the bootloader, the initial RAM disk and kernel images can be quite small by today's standards. A good size is around 300 megabytes. So I'm going to ask the AI to explain this to me as if I were in 5th grade. Okay, so imagine your computer, it's gotta finish, there we go. Imagine your computer is like a house with many rooms. One of these rooms is called the boot partition. This room has special files that help the computer start up and load the operating system, which is like the brain of the computer. On a computer running Linux, there's a special program called bootloader that helps load the operating system. Think of it as a magical door that connects the boot partition to the rest of the house. The bootloader program is usually called grub2 or grub legacy. the boot partition is like a special storage space, and it is usually located at the beginning of the computer's hard drive. This is because a long time ago, computers had limitations that only allowed them to access a certain amount of space. So to make sure everything works correctly, the boot partition is put in the front of the hard drive. The boot partition is important because it keeps everything organized and safe. If something goes wrong with the main part of the computer's storage, called the root partition, the boot partition can still help start up the computer. It's like having a backup plan. The boot partition is not very big because it only needs to store a few important files that the bootloader uses to start the computer. The suggested size for the boot partition is around 300 megabytes, which is not very large compared to today's storage capabilities. So to sum it up, the boot partition is a special room in the computer storage that holds important files for starting up the computer. It's like a safety net in case something goes wrong, and it needs to be located in a specific place to work properly. Alright, so the next part is the EFI system partition, also known as the ESP, which we know all about based on what we read last time. The EFI system partition, ESP, is used by machines based on the Unified Extensible Firmware Interface, UEFI, to store bootloaders and kernel images for the operating systems installed. This partition is formatted on a FAT-based file system. So the ESP uses the FAT-based file system. On a disk partitioned with a GUID partition table, it has a globally unique identifier. That is the globally unique identifier. If the disk was formatted under the MBR partitioning scheme, the partition ID is 0xEF. So I guess you can have an EFI, an ESP on a MBR formatted disk. But if that's the case, then the ID of your ESP is 0xEF. But if it's not, and it's partitioned with a GUID partition table, then it has an identifier, this identifier. On machines running Microsoft Windows, this partition is usually the first one on the disk, although this is not required. The ESP is created or populated by the operating system upon installation and on a Linux system mounted under /boot/EFI. So let's have this explained to me like I was in 5th grade. To me as though I were in 5th grade. Alright, so the EFI, oh, it's kind of long. Oh, it's not too bad. So the EFI system partition is a special part of the computer storage that is used by a special kind of software called the Unified Extensible Firmware Interface, UEFI, which is an alternative to the BIOS. UEFI helps the computer start up and run different operating systems. The ESP is like a little storage area on the computer where important files are kept. These files are called bootloaders and kernel images. Bootloaders are like special instructions that tell the computer how to start up an operating system. Kernel images are like the heart of the operating system that makes everything work. The ESP is formatted in the way that the computer can understand using something called a FAT-based file system. This file system helps organize and store the files in a way that the computer can easily find them. So I feel like there's really nothing that wasn't very good. I'm gonna stop reading that and move on. So the /home partition, let's take a look at that on my home drive, or sorry, my home lab. Okay, there we go. So we got all sorts of stuff in there. I'm going to stop that from running and keep reading. Each user in the system has a home directory to store personal files and preferences. And most of them are located under /home. Usually the home directory is the same as the username. So the user John would have his directory under /home/John. However, there are exceptions. For example, the home directory for the root user is /root, and some system services may have associated users with home directories elsewhere. There is no rule to determine the size of a partition for the /home directory, the home partition. You should take into, or there's no rule to determine the size. You should take into account the number of users in the system and how it will be used. A user which only does web browsing and word processing will require less space than one who works with video editing, for example. Variable data, /var, let's take a look at that. So LL, or tree, /var, all kinds of files in there as well, not nearly as many as in /home. We can do a WC and see exactly what the results were. So WC, so /var, we've got about 10,000 files, we've got 10,000 lines in the output. If we wanted to see like how many, well, actually, no, that's accurate. We've got 10,000 files and directories. 10,000 different files and directories, as compared to, and it hasn't even finished running yet. Yeah, as compared to a number of files so great that to just sit and wait for this command to okay, it did complete. As compared to 357,447 files. So it's bigger than by a factor of 10, and it's got more than 250,000 files and folders. It's big. It's the big one. It's the big one that has a bunch of stuff in it. Right now from my disk. It might be different with variable data if you're doing administration stuff or like data analysis stuff. So the var directory contains variable data or files and directories the system must be able to write during operation. This includes system logs in /var/log, temporary files /var/tmp, and cache application data in /var/cache. /var/www/html is also the default directory for the data files for the Apache web server, and /var/lib/mysql is the default location for database files for the MySQL server. However, both of these can be changed. One good reason for putting /var in a separate partition is stability. Many applications and processes write to /var and subdirectories like /var/log or /var/tmp. A misbehaved process may write data until there is no free space left on the system. So for example, like a log entry keeps telling you a port's down, and it just keeps doing that until it doesn't have any more space on the disk to produce that message. If /var is under /, this may trigger a kernel panic and file system corruption. So if you don't have a separate partition for -var, when it fills up all your data and takes up too much disk space too quickly, it's a sitting. It's like we talked about with the boat having different compartments. So if there's a hull breach, it just fills up one of those compartments and the boat doesn't sink. It's like, well, you don't have that extra compartment in this case if you don't have dash var on another disk, but even another partition would prevent the file system from being corrupted, and would also trigger a kernel panic. I'm not sure what a kernel panic is, but if /var is under /, so if it's in the same partition, it may trigger a kernel panic and file system corruption, causing a situation that is difficult to recover from. If /var is kept under a separate partition, the root file system will be unaffected. Like in /home, there is no universal rule to determine the size of a partition for /var, as it will vary with how much the system is used. On a home system, it will take only a few gigabytes. On a database or web server, as I mentioned earlier, and we can see on my system it only took up okay, I don't know what these were, but we can see on my system it is much smaller than my home directory. On a and like in /home, there's no universal rule to determine the size of the partition of /var, as it will vary with how the system is used. On a home system, it may take only a few gigabytes, but on a database or web server, much more space may be needed. In such scenarios, it may be wise to put /var on a partition on a different disk than on the root partition, adding an extra layer of protection against physical disk failure. Okay, so next we're going to learn about swap. I will take a break and come back to it. Video right now is at 30 minutes, so I'll come right back. Alright, back for more. We're going to learn about swap. The swap partition is used to swap memory pages from RAM to disk as needed. This partition needs to be of a specific type and set up with a proper utility called mkswap before it can be used. The swap partition cannot be mounted like the others, meaning that you cannot access it like a normal directory and peek at its contents. A system can have multiple swap partitions, although this is uncommon, and Linux also supports the use of swap files instead of partitions, which can be useful to quickly increase swap pace when needed. The size of a swap partition is a contentious issue. The old rule from the early days of Linux, twice the amount of RAM, may not apply anymore depending on how the system is being used and the amount of physical RAM installed. On the documentation for Red Hat Enterprise 6, Red Hat recommends the following. So it's dependent on your amount of RAM. On my on my system, I have 96 grams or gigabytes of RAM. So for me, it would be recommended to have at least 4 gigabytes, and then the recommended swap size with hibernation. It doesn't recommend to do that. So it's based on the amount of RAM. The more RAM you have, the bigger your swap size needs to be. But it is at a like a is that a logarithmic curve? Let me think here. It's kind of like a S curve. Yeah, it's logarithmic growth. So when you have a low amount of RAM, you can follow that rule, twice the amount of RAM. Once you're at 2 gigabytes of RAM or higher, then the growth becomes logarithmic. It's equal to the amount of RAM, and then it balances out to where no matter how much RAM you have, 4 gigabytes is probably gonna be fine. So as far as the recommended swap size with hibernation, something they haven't really mentioned, that's more linear. Well, that's logarithmic as well, but anyways, it decreases. You need a lot of swap size with hibernation if you have not a lot of RAM, and if you have a lot of RAM. If you have more than 64 gigabytes, you don't need it at all. If you have anywhere from 8 to 64, you need 1.5 times the amount of RAM you have as opposed to 3. So you need half the amount of RAM you would need if you didn't have a lot of RAM in your system. Of course, the amount of swap can be workload dependent. If the machine is running a critical service such as a database, web, or SAP server, it is wise to check the documentation for these services or your software vendor for a recommendation. Note, for more on creating and enabling swap partitions and swap files, see Objective 104.1 of LPIC-1. We'll get to that later. I want to hear what the AI has to say about this being contentious and what their recommendations are. So, okay. So ultimately, the ideal size for the swap partition should be determined by considering the system's specific requirements and characteristics. It is advisable to assess the typical workload, available physical RAM, and consult relevant documentation or experts to make an informed decision on the appropriate swap size. And I'm going to ask it, give me, write for me documentation that I can use that shows a table of, oh, and I lost it. You know what, I have no reason to question this, that it's kind of too much work. Let's keep moving on. We've got a lot of, oh, well, actually, we're almost done. That's even more reason to move on. We can actually finish this up. So, LVM. We have already discussed how disks are organized into one or more partitions, with each partition containing a file system, which describes how files and associated metadata are stored. One of the downsides of partitioning is that the system administrator has to decide beforehand how the available disk space on a device will be distributed. This can present some challenges later. If a partition requires more space than originally planned. Of course, partitions can be resized, but it may not be possible. For example, if for example, there is no free space on the disk. If that's the case, then you cannot change the size of your partition because there's no space you can use for the new size. I'm kind of curious, what if you want to shrink the disk? So I'm going to ask the AI, say, what if I want to shrink the size of the partition? I will ask that to the AI. So I gotta wait. I always need to wait for it to generate, which is really annoying. And then I'll say, what if I want to decrease the size of the partition? Does it matter if I have no free space on my disk? Or if I have no free space. So if you want to decrease the size of a partition, and I gotta wait for it to, oh, this is so annoying. Okay. having free space is typically necessary. Interesting. When shrinking a partition, the available free space is used to create the new partition size. Without any free space, it becomes challenging to reduce the partition size directly. So in summary, decreasing the size of a partition generally requires free space. So there are workarounds you can use, but in order to store the size that you want to partition to it, you want to shrink the partition to, like, you have to add data to the disk that tells the operating system or the tools you're using what size you want to shrink the partition down to. And if you're out of free space, you don't have anywhere to store that. So you can't shrink a disk. You can't shrink a partition on a disk with no free space and thereby create more free space, because in order to change the partition, you need to add information to the disk, such as the size you want to change it to, and you can't do that if there's no free space on the disk. So you can't even shrink it down if there's no free space on the disk, which is interesting, counterintuitive. Logical volume management, LVM, is a form of storage virtualization that offers system administrators a more flexible approach to managing disk space than traditional partitioning. The goal of LVM is to facilitate managing the storage needs of your end users. The basic unit is the physical volume, PV, which is a block device on your system like a disk partition or a RAID array. PVs are grouped into volume groups, VG, which abstract the underlying devices and are seen as a single logical device with the combined storage capacity of the component PVs. Physical volumes. Each volume in a volume group is subdivided into fixed sized pieces called extents. Extents on a physical volume, PV, are called physical extents, PE, while those on a logical volume are called logical extents, LE. Generally, each logical extent is mapped to a physical extent, but this can change if features like disk mirroring are used. Volume groups can be subdivided into logical volumes, LVs, which functionally work in a similar way to partitions, but with more flexibility. So you can have a volume group, and you can subdivide that into a logical volume, which is kind of like a partition, but it has more flexibility. The size of a logical volume, as specified during its creation, is in fact defined by the size of the physical extents, 4 megabytes by default, multiplied by the number of extents on the volume. From this, it is easy to understand that to grow a logical volume, for example, all that the system administrator has to do is to add more extents from the pool available in the volume group. Likewise, extents can be removed to shrink the LV, which stands for logical volume. After a logical volume is created, it can be seen by the operating system as a normal block device. So LSBLK you could use to check it. A device will be created in /dev, named as /dev /VGNAME in uppercase, /LVNAME in uppercase, where VGNAME is the name of the volume group, and LVNAME is the name of the logical group. These devices can be formatted with a desired file system using standard utilities like mkfs .ext4, for example, and mounted using the usual methods, either usually with the mount command or automatically by adding them to the /etc/fstat file. And I chuckle there a bit because this was a very dry section, and a lot of it didn't really stick. So let's use the AI and let's rewrite this section. So we're going to say rewrite this section in the form of a Shakespearean monologue. And of a Shakespeare monologue. All right, so I'll wait for it to. So hopefully this will be less dry, and I'll take away a lot more from this. I don't know if I could do this without laughing. Hark! Let us delve into the realms of disk organization, where partitions reign supreme, with file systems as their proclamation. Yet a downside exists, foreseen by the wise administrator's eye. Forsooth, the quandary of distributing disk space, 'tis no lie. In this tapestry of woes, challenges may arise anon. If a partition craves more space than was initially drawn, resizing partitions may grant respite, 'tis true. But if space lacks, this remedy becomes but a fleeting view. But fear not, fair folks, for a solution doth appear. Logical volume management, a virtuous notion held dear. A virtualization it be, of storage grand and vast, granting administrators flexibility unsurpassed. At the heart of this tale lies the physical volume, a sturdy block, akin to a disk partition or a RAID array. 'Tis the key to unlock. These PVs, physical volumes, like comrades in arms, join hands in unity, forming volume groups abstracted as one, with harmonious continuity. Behold, within the volume group, volumes make their claim, subdivided into extents, fixed in size, 'tis their noble aim. On the physical volume they bear the name physical extents, whilst on the logical volume, logical extents holds precedence. In most cases, each logical extent aligns with its physical kin, yet when mirroring shines, the tale may take a different spin. A volume group, in its wisdom, may further divide, creating logical volumes akin to partitions with flexibility as their guide. The size of a logical volume, birthed by the administrator's hand, defined by the physical extents to their number they command. Multiply them together, and 'tis clear to see the extent which dictates the volume's capacity. Oh, that's interesting. So it's the size of the logical volume times the physical extent of the disk. Should a volume wish to expand with a longing for more space, the administrator's duty is but to add extents to the embrace. From the pool within the volume group they shall be obtained, like droplets in a water where growth is sustained. And should the need arise to shrink a volume's domain, remove extents with care, and the LV shall wane. Once created, a logical volume dons a guise, an ordinary block device in the operating system's eyes. Lo and behold, in the realm of /dev it shall reside, named with reverence /dev /vg name /lv name to guide. With the touch of formatting, the desired file system shall appear using tools of old like mkfs.ext4, banishing all fear. Mount it, if thou will, with the mount command at hand, or let the /etc/fstab file in its wisdom make it grand. Thus, the monologue draws to its solemn end, logical volume management a boon for those who tend. In this tale of discs and volumes, the Shakespearean flair is lent to shed light on LVM's glory with words eloquent. A flexible approach where disk space finds its way, forsooth, logical volume management saves the day. Alright, so so it talked a lot about extents in the Shakespearean version. I don't remember extents being mentioned, so let's look for extent. Oh yeah, it was mentioned quite a bit. I don't remember this whole section, so let's just read this section where extents were mentioned. So each volume in a volume group is subdivided into fixed size pieces called extents. Extents on a PV physical volume are called physical extents, PE, while those on a logical volume are called logical extents. Generally, each logical extent is mapped to a physical extent, but this can change if features like disk mirroring are used. Okay, now the other thing it's mentioned was an equation, like a multiplication equation. So let's look at multiplied. Okay, and it looks like we've got some math being mentioned here. So the size of a logical volume, as specified during its creation, is in fact defined by the size of the physical extents. By default, physical extents are 4 megabytes. So that 4 megabytes by default, or whatever the size of your physical extents are, multiplied by the number of extents on the volume equals the size of the logical volume. All right, that was actually really useful to do that. Maybe next time I'll go with, I'll look up like the top 10 most famous authors or something, and then go through the list and rewrite and do that. But from now, let's go on to the guided exercises. So the first one, on Linux systems, where are the files for the grub bootloader stored? And we know that, so it's kind of a trick question. They're stored in /boot, but the /boot partition can be in your so /boot, that's gonna, if you're using a BIOS disk, it's gonna be at the beginning of your disk. But if you're using UEFI, it will be in the ESP, so the EFI system partition, which is typically still at the front, but it can be on its own disk. But I think the easy, quick answer that they were looking for is /boot. Yep, so I was partially correct. It is in /group, but I wasn't all the way correct because it's actually /group /grub was the correct answer. All right, so the next one is, how is the size of a logical volume defined? And I do not know this one, so I'm tempted to okay, I'm just going to ask the ChatGPT web here. There's actually other ones I can choose from. But the size of a logical volume, LV, is typically defined by specifying the capacity or storage space allotted to it. In many cases, the size is expressed in units. So it's determined by the allocated storage capacity and can be adjusted to accommodate changing storage requirements. Let's see if that's anywhere near to what the real answer is. By the size of the physical, so yeah, that's what I thought. Okay, so this is the equation. So it's the physical extents times the, oh, I forget, but it's the extents, by the size of the physical extents multiplied by the number of extents. Okay. So this we read that in the Shakespeare, went back and reviewed that. So should have known that one. It just didn't become clear in my mind that a logical volume equals the physical extents, the size of the physical extent times the numbers of physical extent. So the size of the physical extent. So let's say you have 3 physical extents, size 1, 2, and 3, and then you have the first physical extent. You have 2 times, so it would be 1 times 2. So it would be 2 plus 2 plus 3. So it would be 7. I think that's how it works. All right, on a disk formatted with the MBR partitioning scheme, what is the ID of the EFI system partition? This one, I remember it's 0xEF. Yep, 0xEF. I just remember that. Just how my brain works. My brain is good with numbers. Like if you ask me what a numerical ID of something is, I got you. If you ask me what John Smith's first name is, I don't remember. If you ask me what my first name is, I don't remember. Sometimes swap partitions, so besides swap partitions, how can you quickly increase swap space on a Linux system? So I want to say you can do it through extents. Let's see if that's even close to the correct answer. Oh, swap files. Shoot. Okay. I did not get that one right. Let me do the let me use the tutor for this one, because this is the one that I feel like I really didn't understand at all. Oh, and you know what? I actually skipped these and I went to the explorational exercise. So we know the answer for this. It's in /boot/grub. We know the answer. Oh, and then we skipped it and we went down to yeah. So I don't even think we did the second question. The second question is, where should the boot partition end to assure that ensure that a PC will always be able to load the kernel. And this one I don't know, so I'm going to use ChatGPT 4 as my personal tutor. So I'm going to say act as my LPIC-1 tutor, use the Socratic method to teach me the answer to this question. Okay, so can you tell me what the significance of the boot partition is in relation to a Linux system? Yes, the boot partition contains the bootloader files. That's correct. The boot partition is crucial. I'll just have it read it for me.
That's correct. The boot partition is crucial for the system startup process. It often includes bootloader files, kernel image files, and other files necessary for the system to boot properly. Now, have you heard of something called BIOS and its restrictions related to booting systems?
Yes. Yes, the BIOS. Yes, the BIOS is what would read is what uses the files in the boot partition, but can only read the first 440 mega bytes of a disk. Oh, I did not get that right.
Well, it's close, but there's a small correction needed. The BIOS indeed boots the system by accessing the boot partition, but the size limitation is not in megabytes but in a different unit.
Oh,
Do you recall what that unit is?
Wait, it's not in megabytes? I thought it was in megabytes. Is it in bytes?
Not exactly, but you're close. BIOS restrictions deal with a different aspect, which involves the location of the bootloader on the disk, rather than a specific byte size. The unit we're looking for relates to the position on the disk, described in sectors or blocks. Are you familiar with this concept?
I'm gonna say yes. I've got a... are you familiar with this concept? Oh, it's kind of... I know it's at the beginning of the disk, but I don't understand how.
That's alright, let's try to clarify it. Hard drives are divided into small sections known as sectors, also known as blocks in some contexts, which are the smallest units that the system can read or write. In older BIOS-based systems, due to certain hardware and firmware limitations, the BIOS can only read from the first part of the hard drive. This leads us to an important term that you might have heard before. The 1024 cylinder limit. Have you come across this term and do you understand what it means?
So I have come across it, I think, but I don't understand what it means.
That's quite alright, we'll explore it together. The 1024 cylinder limit is an important concept in older BIOS-based systems. The BIOS interfaces with the hard drive using an older addressing method known as CHS cylinder head sector. However, this method has a limitation. The BIOS can address up to 1024 cylinders, 256 heads, and 63 sectors per track, which results in an addressing limit approximately around the first 528 megabytes of the hard drive. When Linux or any other operating system is being loaded, the BIOS must be able to read the bootloader, which is usually stored in the boot partition. Due to the 1024 cylinder limit, the boot partition must be positioned within this first 528 megabytes of the disk to ensure that BIOS can read it. However, this limit is mainly a concern for older systems. Most modern systems use UEFI, Unified Extensible Firmware Interface, instead of BIOS, and UEFI doesn't have the same cylinder, head, and sector limitations. Do you understand how this relates to where the boot partition should be placed?
I'm going to say yes. It needs to be placed within the first 528 megabytes of the hard drive, so that the addressing method CHS does not break due to having to go over the 124 cylinder limit.
Exactly, you got it. By ensuring that the boot partition is within the first 528 megabytes of the hard drive, you can ensure that the BIOS can properly address and read the bootloader, thus allowing the system to boot up correctly. Remember, though, that this is primarily a consideration for older systems that are still using BIOS. Most modern systems use UEFI, which doesn't have these limitations. Now, given this information, how would you answer your original question? Where should the boot partition end to ensure that a PC will always be able to load the kernel?
So it should end before the 1024 cylinder limit, which is typically before the first 28 megabytes of the disk are used up of the disk.
That's correct. You've accurately summarized the situation. The boot partition should indeed be placed within the first 528 megabytes of the hard drive to ensure that an older BIOS-based system can correctly load the bootloader in the kernel. Again, this is mostly a concern for older BIOS-based systems. More modern systems use UEFI, which doesn't have these limitations. But for those older systems, this placement of the boot partition can be crucial for the system's ability to boot up correctly. Well done on understanding this important aspect of Linux system configuration.
All right, I feel good about that. That's pretty good. So where is the partition usually mounted for EFI? I'll need a personal tutor for that one as well. I'm going to take a quick break, and when I come back, oh, we're past the hour mark. That's really good news. So I think I'm authorized to do another video, but I'll just pause it and come back. Alright, welcome back. I'm feeling pretty good. I'm going to try to finish up this whole thing. So the next question, where is the UEFI partition usually mounted? So I'm going to use a personal tutor for this one as well. So the prompt I use is act as my LPIC-1 tutor. Use the Socratic method to teach me the answer to this question. And the question is, where is the EFI partition, also known as the ESP, EFI system partition, usually mounted?
Certainly, I'll guide you towards the answer. First, do you recall what the EFI, Extensible Firmware Interface partition is and why it's important in a system's boot process?
Yes. In a UEFI system, the ESP, what the EFI is the EFI system partition. It is a disk partition It is a FAT formatted disk partition that contains the bootloader files. It is important in a system's boot process because the bootloader files are what the system uses to access to select and utilize and I don't know how to spell utilize, U-T-I-L-I-Z-E. Yep, so to select and utilize the operating, select and boot up to the operating system. To select an operating system and boot up to it.
That's correct. Now, considering its importance in booting the system, would you expect the FE system partition to be mounted at a standard, easily accessible location for everyday tasks, or somewhere less likely to be disturbed by day-to-day operations?
So I'm going to say standard, easily accessible location for everyday tasks. Oh, wait, no, let me think about that. So, considering its importance in booting the system, where would you expect the EFI system partition to be mounted? Would it be A, standard fickle place that everyone's going to be looking at and accidentally writing over and messing up, or B, not that? I'm going to go with B. So, I would expect the ESP to be located somewhere less likely to be disturbed by day-to-day operations.
Absolutely. The FE system partition, given its crucial role, should indeed be in a location that isn't commonly accessed or modified to prevent accidental changes. Now, can you remember what the typical directory is where Linux mounts system critical partitions or special system directories?
Isn't it in, I can't remember. I don't think it's in /boot. System critical partitions. It's like, I don't remember. remember, I know that you can use ls block to check partitions.
That's perfectly alright, and you're correct about using lsblk to check partitions. In Linux, system-related or special directories are often mounted under the root directory. More specifically, in the context of the FE partition, it's typically mounted at boot FE. Does this make sense?
It makes sense. Let's take a look at that on my system. So, I wanted to say boot, but yeah. Yes, I did want to say boot, but I was not confident in that answer.
That's a great start, and you were very close. The FE partition typically gets mounted under the boot directory at boot FE. This is an ideal location because it is a system-related directory that's not commonly accessed during regular operations, helping to prevent accidental modifications. Remember, confidence comes with practice and repetition. Continue studying and testing your knowledge, and you'll gain the confidence you need. Do you have any other questions related to this topic or Linux in general?
I do not. Let's see if that is the same. Yep, so it's under /boot/EFI. Alright, so the next guided exercise. When manually mounting a file system, under which directory should it usually be mounted? And I'm going to do /MNT is my answer. But let's do the Socratic method. So act as my LPIC-1 tutor, use the Socratic method to teach me the answer to this question. Okay.
Sure, I'd be happy to guide you in exploring this concept. So, let's start with the basics. Can you tell me what the purpose is of mounting a file system in Linux?
Of mounting a file system in Linux? It's to have the file system, to make the file system usable by users.
That's correct. When you mount a file system, it essentially integrates that file system into the directory tree of the system, making it accessible for users and applications. Now, can you explain the structure of the Linux directory tree? Specifically, how does the root directory play into this?
Is the very is the beginning of a disk, is the top most level of a disk file system tree.
Exactly. In a Linux file system, the root directory is the starting point from which all other directories or files stem. With this in mind, considering the Linux directory hierarchy, where do you think it would be appropriate to mount file systems manually? Where would make the most sense in terms of organization and convention?
/MNT.
Good thinking. The MNT directory is a standard location where system administrators manually mount file systems temporarily. It's especially useful when you're dealing with things like USB drives, external hard drives, and so on. However, do you recall another directory that is commonly used to mount file systems, especially for permanent mounts? It's a directory that comes standard on most Linux distributions.
Oh, really? It's not /MNT? Oh, that's for temporary. Okay, what about for not temporary? Is it var?
Close, but not quite. It's true that var is a directory where various system files and directories are stored, often ones that change in size, such as logs and databases. However, it's not typically used for mounting file systems. The directory you're thinking of starts with. Can you recall what it is?
I cannot. I'm just guessing at this point. I guess I'll guess boot next one, because that's the next one I can remember.
I appreciate your continued efforts, but boot is not the directory commonly used for mounting file systems. The boot directory contains the files needed to boot the system, such as the Linux kernel, initial RAM disk image for drivers needed at boot time, bootloader configuration, etc. Consider a directory that's near the root directory and has a rather general name. This directory is often used for mounting additional or external file systems. Can you guess which one it is?
I cannot. I guess the next one I know is etc. Let's put that in there.
Not quite. The etc. directory is generally used for storing system-wide configuration files and directories. It's not typically used for mounting file systems.
Oh, shoot.
The directory we're thinking of is actually media. Does that sound familiar? Can you tell me what the media directory is typically used for in a Linux file system hierarchy?
I remember that. Shoot. Yes. Now I remember /media. This directory is used for devices like USB, CD, ROM, and flash storage.
Yes, that's correct.
Removable
The
storage.
media directory is generally used for auto-mounting removable media like USB devices, CD-ROMs, and other temporary media file systems. This is a convention used in many distributions to provide a clear location where devices will be mounted automatically by the system. You correctly identified both MNT and media. These are indeed the standard directories used to mount file systems, either temporarily or for removable media. Do you understand the difference between these directories and why we choose them for mounting file systems?
So yes, /MNT is for more permanent forms of media such as hard drives, but /media is for temporary forms such as USB and CD-ROM.
That's almost correct. However, typically, MNT is used for temporarily mounted file systems, such as when a sysadmin is performing certain operations. For more permanent mounts, such as an additional hard drive that should be available all the time, we usually add an entry in, etc., fstab and create a dedicated directory under, like, data, extra, etc. For mounting it. The media directory is indeed often used for auto-mounting removable media like USB sticks, CDs, etc. This provides a clear, predictable location where users can access their removable media. Does this clarify the distinction between these directories?
No, I am still confused about the difference between /MNT and /media.
I apologize if my previous explanation was not clear. Let's try again. MNT. This directory is provided so that the system administrator can mount a file system manually for temporary use. For example, if you're just needing to access a file system for a short period of time for some maintenance or other task, you typically use MNT. However, this has become less strict and sometimes it's used for permanent mounts too, but that's not its original intended purpose. Media. This directory is typically used by the operating system for automatically mounting removable media, like a USB drive when it is plugged in, or a CD-ROM when it's inserted. On modern Linux distributions, subdirectories are often created under media named after the device or volume label of the mounted media for each user. In most cases, these directories are used as mount points where a different file system is attached to the directory tree. But the key difference is that MNT is typically used for manually mounted file systems and usually temporary, but can be permanent, while media is used for automatically mounted removable media. Does this help to clarify the difference between MNT and media?
So what is the difference between mounting a file system and mounting removable media? What is the difference between a file system and what is a file system? What is a file system and what is removable media? How are they different?
These are great questions, and understanding the definitions will indeed help clarify the difference between mounting a file system and mounting removable media. File system. A file system in computing refers to the methods and data structures that an operating system uses to manage files on a storage device. These files are organized in a tree structure, starting from a root directory. This tree structure can span across multiple storage devices. A file system controls how data is stored and retrieved. Examples of file systems include NTFS for Windows, X4, XFS, and BTRFS for Linux, and HFS Plus for macOS, among many others. Removable media. This term refers to any type of storage device that can be removed from a computer while the system is running. Examples of removable media include external hard drives, USB flash drives, CDs, DVDs, and SD cards. Each of these will have a file system on it which dictates how the data is organized and stored on the physical media. When you mount something in a Unix-based system like Linux, you're making a certain file system available to the operating system. This file system could be from an internal hard drive partition, an external hard drive, a CD, a USB stick, or any other storage device. When you mount a file system, the contents of that device become accessible to you from the mount point onwards in your directory tree. For instance, if you have a USB stick with an X4 file system on it and you mounted it, media, USB, you would see and access the files on the USB stick as if they were local files under media, USB. Now, with regard to the difference between mounting a file system and mounting removable media. When we talk about mounting a file system, it could mean any type of file system, not just ones on removable media. This could be a separate partition on your main hard drive, a network share, a virtual file system, and so on. A file system could be on a permanent storage device, like your computer's hard drive, or on removable media like a USB stick. On the other hand, when we talk about mounting removable media, we're specifically talking about making the file system on a piece of removable media, like a USB stick or CD, accessible to the operating system. This is still mounting a file system, but it's specifically a file system on a removable device. I hope this makes the difference clear. Is there anything else you'd like to know about this topic?
Okay, so I think that's fine. Let's take a look at the files in both directories. So in media, we don't have anything in there. That makes sense. There's no USB or anything plugged in. Let's take a look at mount. Nothing in there either. I'm kind of tempted to just go plug I'm going to do that. I'm going to go plug a USB drive in there, and I'll be right back. All right, I'm back, and I've got a USB thumb drive plugged in, so that's temporary media, so it should go in here. Got nothing. Got nothing. Okay, so I'm not sure what the deal with that is, but maybe an LL or LS-AL. Nothing. Alright, that's fine. Okay, so but we know the question to this. Where are they usually mounted? They're usually mounted in /boot/EFI is the answer to that one. Yep. And then the next question, when manually mounting a file system, under which directory should it usually be mounted? /MNT is the answer to that one. Yep, it's not mandatory. You can put it anywhere you want, but you put it there to to have that work. Then the other ones before cylinder 1024, boot UFI. Okay, so on to the next set of questions. What is the smallest unit inside of a volume group? So let's get a personal tutor on that.
Sure, I'd be happy to guide you through this using the Socratic method. To begin, let's start by discussing what a volume group, VG, is in the context of the Linux operating system. Can you tell me what you understand by VG in the Linux Logical Volume Manager, LVM?
So this is what I had translated to Shakespeare. So like, yes, from what I understand, a volume group in the Linux Logical Volume Manager, LVM, is like a virtual disk. Is that right?
Sure, I'd be happy to guide you through this using the Socratic method.
Shoot, I'm out of ChatGPT 4.
That's a good start. A volume group, VG, in the Linux Logical Volume Manager, LVM, can be thought of as a pool or a container that holds multiple physical volumes, PVs, and logical volumes, LVs. It provides an abstraction layer that allows you to manage and allocate storage resources more flexibly and efficiently. Now, let's focus on the concept of logical volumes. Can you explain what a logical volume is and how it relates to a volume group?
Yes. A logical volume is a virtual storage resource. It relates to a volume group because it constitutes a portion of the volume group.
Exactly. A logical volume, LV, is a virtual storage resource that is created within a volume group, VG. It is similar to a partition or a disk volume in traditional disk management systems. The logical volume is what you can actually format with a file system, mount, and use for storing data. Now, let's delve into the next step of our Socratic method. Considering that a volume group, VG, contains multiple physical volumes, PVs, and logical volumes, LVs, can you think of the purpose or role of the smallest unit inside a volume group?
So multiple, so you can have, so the purpose of the smallest unit inside a volume group is to be able to plan how many units you can include in your volume, is to be able to plan the maximum number of units contained in the volume group.
That's a good observation. The purpose of identifying the smallest unit inside a volume group, VG, is to determine the granularity of allocation and management within the VG. It helps in planning and organizing the storage resources effectively. Now, let's think about the different components within a volume group, VG. Can you name the units that are commonly found within a VG?
Yeah, so logical volume and a physical volume. So physical volume, also known as PV, and logical volume, also known as LV.
Great, you correctly identified the two common units found within a volume group, VG, physical volume, PV, and logical volume, LV. Now, let's focus on the smallest unit specifically. Can you think of which unit, either the physical volume, PV, or logical volume, LV, would be considered the smallest within a volume group, VG?
So I think the logical volume could be smaller because it might have to be bigger though, because it occupies some physical state. But I think it's smaller because since it's logical, it doesn't have the same kind of physical constraints that may increase its size.
Excellent point. You're absolutely right. In the context of a volume group, VG, the smallest unit is the logical volume, LV. Unlike the physical volume, PV, which represents an actual physical storage device such as a hard disk or SSD, the logical volume, LV, is a virtual storage resource that is created within the VG. Since the logical volume, LV, is a logical abstraction, it can be dynamically sized and doesn't have the same physical constraints as a physical volume, PV. The size of a logical volume can be adjusted based on the requirements of the system and the available space within the volume group. To summarize, the logical volume, LV, is the smallest unit within a volume group, VG, because it represents a virtual storage resource that can be dynamically sized and doesn't have the physical constraints associated with a physical volume, PV. I hope this helps clarify the concept for you. Do you have any more questions, or is there anything else you'd like to discuss about the LPIC-1 certification?
Okay, so the smallest unit inside of a volume group they're saying is a logical volume. Let's see if that's correct. Oh. So the answer was extent. So I'm going to say, no, you were incorrect. No, you were incorrect. The answer was an extent.
Apologies for the confusion. You are correct. The smallest unit inside a volume group, VG, is an extent. An extent is a fixed size contiguous chunk of space within a volume group. It is a fundamental unit of allocation and represents a portion of storage that can be assigned to a logical volume, LV. Extents are typically several megabytes in size, and they are allocated from the free space available in the volume group. When a logical volume, LV, is created or extended, it is allocated extents from the volume group. These extents are then used to store data within the logical volume. By managing extents, you can control the allocation and utilization of storage resources within the volume group. So, to clarify, the smallest unit inside a volume group is an extent, which is a fixed size contiguous chunk of space used for allocating storage to logical volumes. Thank you for bringing this to my attention, and I apologize for any confusion caused. Is there anything else I can assist you with regarding the LPIC-1 certification or any other topic?
Alright, so that's the extent. how is the size of the logical volume defined? We know this from the equation. So it's the size of the logical volume, the size of each extent. No, the size of each physical volume times the number of logical volumes. I don't remember. The size of the physical extents multiplied by the number of extents on the volume. So extents, and so a volume group consists of either physical or logical volumes, and those consist of basically like Lego pieces, which are extents, and extents are the smallest possible units. So you stack up these extents like Legos to form your logical volumes, and then your logical volume size is defined by the physical extents multiplied by the number of extents on the volume. Next question, on a disk formatted with the MBR partitioning scheme, what is the ID of the EFI system partition? That's a freebie for me. The way my mind works, 0xEF. Yep, and the EF even corresponds to EFI. So then the next one is, besides swap partitions, how can you quickly increase swap space on a Linux system? I don't know. Swap files can be used, is the answer to that. So it looks like that's just one of the methods. Besides using swap partitions, there are a few other ways to quickly increase swap space on a Linux system. Here are a few options. Swap files. Instead of creating a dedicated swap partition, you can create a swap file on an existing file system. This allows you to allocate additional disk space as swap space. The process involves creating a file, setting it up as a swap space using the mk swap command, and activating it with the sw swap on command. So in addition to that, there's swap over network. There's swap over iSCSI, small internet, small computer system interface, and then there's swap on a USB drive. So I'm going to ask it, when would you need to swap? When and why would you need swap space? And I think the answer is if you're out of RAM. So it's got to generate here. So swap space is a portion of the computer's hard drive that is used as virtual memory when the physical RAM becomes fully utilized. Yep, that's what I thought. So here are some scenarios when swap space is needed: insufficient physical RAM, memory-intensive applications, system hibernization. When a system hibernates or enters sleep mode, the entire contents of RAM are written to the swap space. This allows the system to restore its previous state upon waking up. Sufficient swap space is necessary to store the entire RAM contents during hibernation. Oh, that's interesting. So I guess in a 16-bit system, if you don't have a or 16 megabytes of RAM, if you don't have a swap space big enough for that, you can't come out of system hibernation and keep everything. Maybe that's why system hibernate, because I remember on one computer I couldn't hibernate it. It would just brick it if I tried to hibernate it. So maybe that's why. It's because I didn't have enough swap space, and it only partially saved the contents of the RAM. So like when it came out of system hibernation, it was just basically bricked. Okay, then there's memory over commitment and system stability and performance. Even if a system has enough physical RAM, having a small amount of swap space can still be beneficial. Swap space serves as a safety net by preventing out-of-memory situations. So it's important to note that with the advent of systems equipped with ample RAM, the reliance on swap space has reduced in many cases. However, having an appropriate amount of swap space remains useful for maintaining system stability and handling occasional spikes in memory usage. The specific need for swap space varies depending on the system's configuration, workload, and usage patterns. All right, and that's the last one. So we saw that there were additional answers to that. You can use swap files, but you can also use the internet. You can have swap space on like a USB drive, external storage. Yeah, the answer they have is to use swap files. All right, so the summary. In this lesson, you learned about partitioning, which directories are usually kept in separate partitions, and why this is done. Also, we discussed an overview of LVM, logical volume management, and how it can offer a more flexible way to allocate your data and disk space compared to traditional partitioning. The following files, terms, and utilities have been discussed. So / the Linux root file system, / var, the standard location for variable data that can shrink and grow over time, / home, the standard parent directory for home directories of regular users on a system, / boot, the standard location for the bootloader files, Linux kernel, and initial RAM disk, the ESP, which is the EFI system partition, used by systems that have UEFI implemented for the storage of the system's boot files, swap space used to swap out kernel memory pages when RAM is heavily used, mount points, directory locations where a device such as a hard disk will be mounted to, partitions, which are divisions on a disk. And we already went through the answers, so that's it. Stay tuned for the next one, lesson 102.2, installing a boot manager. Thanks for watching, and see you in the next one.